this is lecture 33 of condensed matter physics 1, and we have been discussing electrons in a periodic potential. What I showed you yesterday, and rather argued, that if you have electrons in a periodic potential VR, where VR is periodic with respect to crystal distances, then you mix for the wave function the plane waves of I k dot r for any k, and the other one that we mixed was k plus or minus n g e raised to I k plus n g dot r. So, what it means is that with a plane wave e raised to I k dot r, we can mix plane waves of the wave vector k plus n g r, and the example that we took was two plane waves mixed, and we took psi r to be c in 1D k e raised to I k x plus c k minus 2 pi by a e raised to I k minus 2 pi by a x for k greater than 0, and psi r equals c k e raised to I k x plus c k plus 2 pi by a e raised to I k plus 2 pi by a x for than 0. And this was based on perturbation theory. In general, I also said that if you go beyond the first Brillouin zone, you are going to have psi, which is a mixture of e raised to I k x and e raised to I plus minus n g, where g is the smallest lattice vector x. Let me remove the vector sign from top of g. We are now going to make this rigorous in this lecture through the proof of Bloch's theorem. So, this lecture is devoted to form of wave function for electrons in a crystal, and this is given by Bloch's theorem, which is essentially that you can form a wave function in this crystal or in a periodic potential by mixing plane waves for a given k and by adding to it only the reciprocal space vectors of the given crystal. No other wave vector can be added to it. So, let me just first show it for two wave system that we took. For two waves, suppose I take a psi x to be some c k e raised to I k x plus some key c k prime e raised to I k prime x, and k prime is not equal to k, and k prime is not equal to k plus some n g. It's some arbitrary k prime. Then I am going to show this will imply that C k and C k prime are both 0, and that means the wave function cannot exist where you take this kind of form where k and k prime differ by some arbitrary wave vector. So, again let me go back and write h psi equals E psi, and h is minus h cross square over 2 m, since we are talking about a single dimensional system, and this is equal to summation n times 2 pi by a V n e raised to I 2 pi by a n x. This is the form of the potential, and therefore, when I write the substitute psi in h psi, h operating on C k e raised to I k x plus C k prime e raised to I k prime x, I am going to get epsilon k C k e raised to I k x, that is the first kinetic energy term operating on it, plus epsilon k prime C k prime e raised to I k prime x, plus summation n times 2 pi by a V n e raised to I 2 pi by a n x times C k e raised to I k x plus summation n 2 pi by a V n e raised to I 2 pi over a n x C k prime e raised to I k prime x equals E times psi. So, I have written the Schrodinger equation here, and then you bring the right hand side to the left hand side. Let me just remind you, I am writing h psi equals E psi with psi equals C k e raised to I k x plus C k prime e raised to I k prime x with periodic potential. Then I get epsilon k minus E C k e raised to I k x plus epsilon k prime minus E C k prime e raised to I k prime x plus summation n all that V n da, 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 equals 0. Let me now multiply by e raised to minus I k x dx and integrate. I am going to get epsilon k minus E C k. Since k is not equal to k prime, the other terms are going to give me 0. Let this be an exercise for you. And this shows that C k is 0, since epsilon k, which is equal to h cross square k square over 2 m, is not equal to E. It cannot be equal because we have a potential. And similarly, for C k prime, we show that C k prime is also equal to 0. So, if k and k prime differ by more than 0, but they are different by other than reciprocal lattice space vectors, then the wave function becomes 0. So, it cannot exist for that. You have to mix only k and these reciprocal space vectors. Let us do that now. So, let me, and that will give you a proof of Bloch's theorem also. So, let me take in 3D, these are all arguments. Now, I am going to do rigorous mathematics. H equals minus h cross square over 2 m del square plus this periodic V, which is equal to minus h cross square over 2 m del square plus summation n V n e raised to I n. G is the smallest reciprocal space vector n g. So, this is all kind of symbolic. N g gives you all different kinds of vectors. So, now I am going to take, again I argued that k and k prime have to be differing only by a g, but I am going to take psi r to be summed over some k's c k e raised to I k dot r. And hopefully by now, through previous lecture and this, you understand that I can make the expansion of the wave function in terms of plane waves. Now, let us go to the Hamiltonian, which is minus h cross square over 2 m del square plus summation. Let me go back to Kittel's notation. Now, I will take this g to be all lattice vectors and write this as V g e raised to I g dot r. Earlier I was writing n to just be very clear about it. So, let me note here, note g is a general reciprocal lattice vector. This is just to keep the notation simple. You substitute psi in h. So, I am going to get h psi equals summation over k epsilon k c k e raised to I k dot r. Just a reminder on the side that epsilon k is h cross square k square over 2 m plus summation over k summation over g V g e raised to I k plus g dot r, that is the potential term, and this should be equal to E summation over k c k e raised to I k dot r. You bring the right hand side to the left hand side and you get h psi minus E psi, which should be 0, and this can be expanded as summation over k epsilon k minus E c k e raised to I k dot r plus summation k summation g V g e raised to I k plus g dot r is equal to 0. That is the equation. Now, I will multiply again by e raised to minus I k prime dot r and integrate this equation. Taking proper care of normalization and all that, what you get on the left hand side is going to be summation k epsilon k minus E delta k prime k plus summation k summation g V g e raised to I k prime with a minus sign plus k plus g dot r dr, which is nothing but summation over k epsilon k minus E, or there is a c k here, c k delta k prime k plus summation over g V g delta k prime comma k plus g is equal to 0. This is true for each k. So, let me write this on the next page. What you have gotten by writing h psi minus E psi equal to 0 is summation k epsilon k minus E C k delta k prime k plus summation g V g C k delta k prime minus k minus g is equal to 0. Just keep checking for the consistency from the previous page to this, where I have used integration k minus k prime dot r dr with proper normalization equals delta k prime. This then goes to I sum over k epsilon k prime minus E C k prime, this was C k, plus summation over g V g C k prime minus g is equal to 0. That is the equation I get from here after summing over k. And since k prime is a dummy variable, it could be anything. I will just simplify the notation and write it in terms of k as epsilon k minus E C k plus summation over g V g C k minus g equals 0. That is the equation we get from this. Now, since we write psi as summation over g e raised to I k plus g dot r times C k plus g, I can write this equation for anything. I can write this for k, I can write for this k plus g, I can write this for k minus g, and so on. So, the set of equations that I get are going to be E, let me write 3 of them, k plus g minus E, C of k plus g plus V minus g C of k, I have taken g to be minus of that, plus let us say V minus 2 g C k minus g, and so on equals 0. If I take that k to be the k prime to be k, I would get epsilon k C k plus V minus g C k plus g, and on the other side I can take it to be minus g. This is minus E also, and then I will get V minus g C plus g C k minus g equals 0, and I can add all other terms. So, this is a set of linear equations that are to be satisfied and get non-trivial k and k plus g by solving them. So, what I am getting is from the Schrodinger equation, we get a set of linear equations. And let me just write this once in the form of a matrix. Suppose this is k plus 2 g, k plus g, k minus g, k minus 2 g, and the labels are k plus 2g, k plus g, k minus g, k minus 2g. I am not bothering to put the vector signs. Then what I am going to get is the diagonal term is going to be E, k plus 2g minus E. This is going to be V, g, V, 2g, V, 3g, V, 4g. Here I am going to get the next line minus V of minus g, E epsilon k plus g minus E, V of g, V of 2g, V of 3g. Next, I am going to get V of minus 2g, V of minus g, epsilon k minus E, V of g, V 2g, and so on. And out here, I am going to get C k plus 2g, C k plus g, C k minus g, C k minus 2g equals 0. And this is going to be an infinite by infinite dimensional. To get solution, you should have the determinant of the matrix equals 0, and that gives you eigenvalues E, infinite number of them. So, for each k I am going to get tons of eigenvalues depending on how many waves I am mixing, and for each eigenvalue I am going to get Ck plus g, Ck plus 2g, which will determine the wave function in terms of the expansion in terms of the plane waves. So, let us just quickly check against two plane wave mixing that I did in my 30-second lecture, where I had taken psi to be C k e raised to I k x plus C k minus 2 pi by a e raised to I k minus 2 pi by a x, g is 2 pi by a. In this case, the matrix would be epsilon k minus E, V 2 pi by a, V minus 2 pi by a, epsilon k minus 2 pi by a minus E, C k minus 2 pi by a equals 0. So, this checks, and this determinant equals 0 gives E, and this is precisely what we did last time. So, this whole thing checks. So, now the entire thing is very clear that you take the Schrodinger equation, which is periodic, which has periodic potential, then the only waves that mix when I expand the wave function in terms of plane waves for a given k are k, and you add the reciprocal space vector to it, and then you get an equation. You diagonalize, or you take the matrix of this you diagonalize the matrix. In other words, you take the determinant of the matrix to be 0, and that gives you the eigenvalues for each k, and the coefficients then lead to the wave function. That is the whole thing. Now, this I will use now to prove rigorously the Bloch's theorem. So, let me just summarize. H psi equals E psi with H equals minus h cross square over 2 m del square plus V r, and V r is periodic with the lattice vector. Then take psi to be of the form C k e raised to I k dot r. This gives psi equals summation G C G e raised to I k plus G dot R. G is reciprocal space vectors, and then the equations come. Central equation, that equation that I wrote is known as central equation, gives central equation, and solution gives E as a function of k and psi r. Now, let us write Bloch's theorem. The statement is stationary state wave function of Schrodinger equation for periodic potential V r satisfy psi r plus r equals e raised to I k dot r psi r. Being a crystal or lattice vector. That is the statement, and by now you should be seeing it very easily that this is indeed so, and let me show it to you explicitly. So, we have written psi r as equal to C g, this is for each given k, e raised to I k plus G dot r. Let me write psi r plus r, which is equal to summation of G C g e raised to I k plus G dot r times e raised to I k plus G dot r. Now, from definition I know that e raised to I G dot r is equal to 1, and therefore, what you are left with this equal to e raised to I k dot r I can take out summation G C g e raised to I k plus G dot r, which is e raised to I k dot r psi r. That is the statement of Bloch's theorem, proved. I just want to make a note here. Bloch's theorem in this case is a special case of a general differential equation known as Hill's equation. You may want to look it up in your mathematics books. So, this is nothing but Hill's equation. This will be true in any periodic kind of driving term, right. So, that is what it is. Now, let me just write some properties and some observations about Bloch's equation. So, some comments and observations about Bloch's wave function, and therefore, this is going to be useful in discussing electronic properties of these systems. 1. Psi r, which is given as summation g e raised to I k dot k plus g dot r c g, can be labeled by k as k determines the transformation of psi r. K is the only quantity that tells you how psi behaves if you go from one point to the other. Therefore, I label it by k. Just one more comment. If you go back to that 2 plane wave solution in 1D, I had the energy bands like this. So, the wave function out here I am labeling by k as well as a band index n. So, I can label psi as k, that determines how this is transformed, but I will also put a label n, which is the band n wave function. Point number 2, k is defined or taken, not defined, taken to be within the first Bloch zone. Why? Because if I take psi k plus g r for any n, it will be equal to summation again all over g c k plus g e raised to I k plus g plus some other g, let us call it g prime dot r. I can always shift g, it does not really matter. This is g prime is a dummy variable. So, I can start anywhere. More importantly, if I take psi k plus g r plus r, this will be equal to again psi r times e raised to I k plus g dot r, but e raised to I g dot r is 1. So, this is again going to be e raised to I k dot r psi r, because e raised to I g dot r is equal to 1. And this implies label k and k plus g give the same transformation property of psi k r. So, I can label it by k, I can label it by k plus g or whatever, it does not matter. So, this I can label the wave function by anything. So, I can restrict myself to first Bloch zone in taking k, and this also implies therefore that k can be taken to be in the first Bloch zone. I want you to recall exactly the same situation for phonons, where we showed that the displacement of atoms is the same whether I take k within the first Brillouin zone or add a reciprocal lattice vector to it. It does not really make a difference. Exactly the same situation prevails here. Now, this should not be surprising to you, because in both the cases I am solving an equation which has a periodic driving force, and as I said, there is a general Hill's equation that gives you this general solution. So, properties of solution should be independent of what kind of driving force or what kind of system I am talking about. So, that is the kind of mathematical structure one is talking about, that there is a periodic driving force. So, property should be the same. And in this periodic system, the displacement in the case of phonons or the wave function in case of electrons can be labeled only by k in the first Brillouin zone. Going further on this, when I write the wave function as psi k r, a note of caution, h cross k is not the momentum of electron in psi k r. Why? Because pure momentum state is e raised to I k dot r. What you have here is psi k, which is a mixture of C k plus g dot r, mixture of many momentum states. So, it cannot be an eigenfunction of the momentum state, and therefore, h cross k is not the momentum. However, k being the label, and you will see that in the crystal k plays an important role, and at times role like the momentum of the electron. Point number 3. Central equation gives a way of obtaining the wave function and the corresponding energy E by taking a finite number of plane waves. More the number of plane waves taken, more precise is the solution. Ideally, I should be taking an infinite number of plane waves, but that cannot be solved. So, example that we took was 2 plane wave mixing. I will give you in your assignment to solve by taking more and more plane waves, and more you take them, better the solution would become. But maybe you want to cut off at a certain point beyond which the accuracy is not improved that much, or it is not improved to the point where you can check it. Now, I will also give you an assignment, a way of solving Schrodinger equation for V r periodic by integrating it in 1D. This is something I had developed, and I like you to solve it. It gives you solution just like you solve for atoms or molecules by integrating the Schrodinger equation. We will be doing that also. It is an interesting way of solving the Schrodinger equation. So, there are 2 ways you can solve it. I will give you both the problems in the assignment. Point number 4, So, restricting oneself to taking k in the first Bloch zone, you write wave function psi n k r, which satisfies psi n k r plus r equals e raised to I k dot r psi r, and gives energies E in the nth band as a function of k. And we saw this example in the previous lecture, lecture 32, where when we solved it, the first band came out to be like this. The second one I had said was like this kink here. If you take only 2 plane waves, but you take more and include everything, you will get it like this, and third one will come like this, and so on. And you restrict yourself to within the first Bloch zone. So, these are 4 points I made about the Bloch wave function. So, notice whatever we discussed in lecture 32 has now been made rigorous and exact through this Bloch's theorem. Now, I am also going to give you now an alternate proof of Bloch's theorem, and this will be based on discrete translational symmetry of H. Hamiltonian, which is minus h cross square over 2 m del square plus V r, where V r is periodic, remains the same. If lattice is shifted by r. So, what one is saying is that if I had this lattice, I am showing it in 1D, and I shift it by one lattice vector, or shift it by one lattice vector the other way, or shift it by 2 lattice vectors, the whole thing looks the same. I can now add, doesn't change, and therefore, the solution should not change in the way that it changes the physical properties. So, what I would then say is that, just to be consistent, let us erase this and draw it thin. Okay. So, if I shift the crystal, the wave function psi r should at most become a constant times psi r, because the Hamiltonian has not changed, but there has to be some change. This becomes c times psi r. So, this is shifted by r. So, let us say psi shifted by r becomes c times psi r. Psi shifted by 2 r will become c square psi r, therefore. And so on. So, let us see now is if this keeps on happening. So, let us write r plus r becomes psi r plus r c. and this is c square. Now, as you shift the lattice, the wave function cannot grow or cannot come down, right. It's so psi r plus r cannot grow like this and cannot diminish from one place to the other. And this implies, this therefore means that mod c has to be 1. It cannot be a real number therefore, and this implies I am going to write c equals e raised to minus I k dot r. And this satisfied if I do it twice, e raised to minus I k dot 2 r is nothing but c square, and mod c is 1. So, if I shift the lattice, by r, wave function psi r becomes e raised to minus I k dot r psi r. And now, I do not shift the lattice, I shift myself. This implies if I jump from one point to the other, the wave function will change like e raised to I, this is r, k dot r psi r, and this is Bloch's theorem. This also implies, sometimes it is also written a slightly different way, that wave function of periodic potential is psi k r equals e raised to I k dot r u k r, where u k r is periodic. So, let me write this separately in the next sheet. Alternate statement of Bloch's theorem is that psi k r is equal to e raised to I k dot r u k r, where u k r is periodic with the crystal periodicity. So, I have given you two different proofs of Bloch's theorem. I have given you alternate statement of Bloch's theorem, right. So, this is the general property, and I have given you 2 or 3 properties. Now, finally, I want to do counting of states or Bloch states. Now, see, I wrote the form of Bloch wave function psi k r equals e raised to I k dot r u k r. Counting, we again apply periodic boundary conditions, just like we did for plane waves or just like we did for phonons. There is a e raised to I k dot r function, so periodic boundary conditions come in handy, and we say that psi k r plus some n r is equal to psi k r, and this gives you e raised to I k dot n r equals 1. And this immediately implies, like in free electron, that k x is going to be 2 pi over whatever L x is, n times n. K y is going to be 2 pi over n L y n, and k z is going to be 2 pi over n L y n, where n is 0 plus minus 1 plus minus 2, and this is all restricted to the first Bloch zone. So, it is exactly like the free electron boundary condition. The K's are defined exactly like free electrons, and therefore, number of K points in a BZ is exactly equal to n, or n by a L by a, where n is equal to number of cells over which periodic boundary conditions have been applied, and equivalently in 1D L equals N A, the length over which periodic boundary conditions have been applied. So, K is quasi-continuous. You heard this term earlier also in terms of in context of free electrons. So, what we are going to have is, if I were to make, I will take one particular band, E k versus k, I am going to have k values at these discrete points. Let me make them bigger. Notice that I have not made it at the last point on the right hand side, and here I am going to make it at the last point. So, here it is, minus pi by a in 1D, pi by a here. I did not make this last point because this is equivalent to this. So, either I count that last point or the last point here, and these number of points is exactly equal to n. And each k state can accommodate 2 electrons, and this implies that each band can accommodate 2n electrons. So, this is all I want to say about Bloch's theorem and the related wave function of Schrodinger equation in a periodic potential or in a crystal. So, let me now conclude the lecture by stating that, number 1, in a crystal, and by that I again mean periodic potential, the solution of Schrodinger equation satisfies psi k r plus r equals e raised to I k dot r psi r, or is of the form psi k r equals e raised to I k dot r u k r, u k is periodic. Number 2, k can be taken to be within the first Bloch zone. Number 3, E and psi can be obtained by solving the central equation with a finite number of plane waves. Number 4, total number of states in a band is n. N is number of cells taken for periodic boundary condition, and therefore, a band can accommodate maximum 2n electron. Thank you.